In this module, we will learn how to model mechanical systems from first principles. Previously, we had learned how to analyze differential equations representing physical systems and how to solve differential equations using the Laplace transform. In this module, we will specifically learn how to generate that differential equation for mechanical systems. The structure of the lecture will follow the outline shown. We'll talk about the different types of elements that make up a mechanical system. We will go through some examples, and then we will talk about how motion is transmitted and converted using gears and pulleys and things like that. Here are two example mechanical systems. The bottom system is a translational system, and then the one above it is a rotational system. We will do both. Each type of system consists of three basic types of elements. One, inertia elements, such as the mass or rotational inertia shown, spring elements, and damper elements. And as we discuss these, the spring elements and the damper elements don't literally have to be springs or dampers. Even a solid bar of steel has stiffness properties and damping properties. Inertia elements are in essence the mass in a translational system, or the mass moment of inertia in a rotational system. Each inertia element with its own independent motion needs its own differential equation to describe its motion. We will use two sort of approaches for deriving the differential equations. One is Newton's second law, which is F equals ma, and then sort of a rotational version of Newton's second law, which is also a form of Euler's second law, sum of the moments equals J alpha. It's interesting to note that inertia elements store kinetic energy, and that can be proven below, where energy is power integrated over time in essence. This isn't something that we're going to use in this class, but if you were to go further and look at modeling systems using state space form, considering where energy is stored in the system can help you derive the state equations for a system. Another type of element common to mechanical systems are spring elements, where the force or torque is generated to resist deflection. Examples of this include springs, but as I said previously, even a steel rod has stiffness. If a steel rod will deform and try and return to its original shape. Again, considering the energy aspect of these elements, spring elements store potential energy, which can be useful if you're trying to derive the state equations of a system. The way that we will typically model the force generated by a translational spring is using Hooke's law. That is, the force generated by the spring is proportional to the deformation of the spring. So if we look at this figure, X, capital X, is sort of the undeformed length of the spring, and the total deformation of the spring is the difference in the motion between the two ends. So X2 describes the motion of the left end of the spring, and X1 describes the displacement of the right end of the spring. Therefore, the total deformation of the spring is the difference between the displacement of the two ends, X1 minus X2. Looking at the spring, you can sort of imagine that if you compressed the spring, it would generate a force to sort of push back on you on both ends, and that's how we're going to model things. So if I compress the spring, a force F will push back on each end. Alternatively, if you were to stretch the spring from its undeformed length, if you were to stretch it, then you'd have equal and opposite forces pulling in on the two ends of the spring. This type of model of a spring, using Hooke's law, is desirable because it's a linear model. The force generated is linearly proportional to the deformation. In reality, all springs are nonlinear. If you stretch the spring far enough, it will, in essence, start to take a set. It may deform plastically. Even though that is the case, this linear type of model tends to work pretty well as long as the deformation isn't too large. If you sort of zoomed in on the origin of this graph, where you were looking at smaller amounts of deformation, the nonlinear graph and the linear graph would sort of lay on top of one another. They'd be very close to one another. Torsional springs we can model in the same sort of manner, where the torque being generated in this case is proportional to the sort of the angular deformation of the spring. So you can sort of imagine this spring as being twisted, where the two ends of the spring are moving with different amounts of displacement, and the torque generated is going to be proportional to the difference in the displacement of the two ends. The last type of element that we will include in our mechanical system models are damper elements. And damper elements, they model how a force is generated to resist motion. And examples of these are dashpots, friction, and wind drag. For example, you can consider if you have an object that's sliding on a surface, friction will be generated to oppose the motion of that object along the surface. Similarly, if you have an automobile moving through air, there will be wind drag generated to oppose the motion of that automobile. Here's an example of a dashpot. This symbol you can sort of envision as being a container filled with some viscous fluid, and a plunger separate of that container that's trying to be pulled through the fluid. And so as you attempt to pull the plunger through the fluid, there's some resistance that's developed, and that resistance is proportional to the relative velocities of the two ends. And so that's what's shown in this equation here. The force generated is proportional, where B is a proportionality constant between the difference in velocity of the one end and the other end. You can imagine if the two ends were moving together with the same velocity, there would be no resistance generated. In essence, the plunger and the fluid would be moving together. You only generate resistance when you try and pull the plunger through the fluid. Analogously, we have a rotational version of the dashpot where the torque is being generated such that it's proportional to the relative angular velocities of the two ends. Again, thinking about how energy relates to a damper element. A damper dissipates energy, so it doesn't store energy, which is different than the inertia elements and the spring elements. In the previous slide, we saw a model of the force generated by a dashpot, and that model was linear, sort of like this model over here, where the force was linearly proportional to the difference in the relative velocities of the two ends. This kind of model also represents a viscous friction model, where the friction generated is proportional to the velocity along the surface. Again, we like this type of model because it's linear. Another type of friction model is a Coulomb friction model, where you have this stiction such that when you try and move an object relative to another object or a surface, it's initially going to stick. And so there's force that's being generated without any motion when the velocity is still zero. But as you increase the applied force, eventually it breaks free. And then at that point, the force is constant. And the direction of the force changes whether you're the direction that the object is going. And so this is a nonlinear model of friction because of the jump. And then here's an example of of a typical type of model for wind drag, where wind drag tends to be proportional to velocity squared, where again we have this sort of nonlinear model. As was mentioned previously, nonlinear differential equations are difficult, if not impossible, to solve analytically. So when we can, we will try and use a linear model. When a linear model isn't sufficient, we will discuss some ways to sort of analyze nonlinear systems. Here's another example of a frictional torque model that's more accurate than either the viscous model or the Coulomb friction model from the previous slide. It's more accurate for most situations in that it contains aspects of both types of models. So we see that the friction, the torque, is linearly proportional to velocity, where here omega is angular velocity. So the faster it's spinning, the larger the force is. But there's also a stiction element to it, which was discussed previously, where it'll initially stick before it breaks free. In this sort of more realistic type model, we will actually see examples like this when we do our laboratory activities. In summary, when we want to model mechanical systems, i.e. when we want to generate the differential equations representing the mechanical systems, we're going to follow this approach. First, we're going to choose a coordinate system and an orientation. Then we're going to draw a free body diagram for each inertia. When we do that, we will note various assumptions, assuming viscous friction or assuming a linear spring, things like that. Then we will generate the equations of motion, i.e. the differential equations, using these two equations we showed previously, Newton's second law on the left and the rotational version of Newton's second law. And then finally, we will attempt to double check our results to verify that our equations of motion, our differential equations that we've generated, make intuitive sense.